Okay, in this problem, we're spinning a wheel twice. So the first spin, the probability that the person wins a poster is the number of poster sectors over the number of total sectors. So if you read the problem, you will see that the number of poster sectors is 10 and the total number is 18. I am reducing that to 5/9. You do not have to reduce it if you're going to give me a percentage for a probability. If you're going to give me a fraction, you don't have to reduce it until the end if you don't want to, but I reduce it on the way because I'm trying to multiply without a calculator. Now we're going to spin the wheel again, and it doesn't say anything about blocking out a certain sector, so we assume we're spinning the same wheel we did this first time, and the probability of spinning for a poster is again 5/9. Multiply straight across. The probability of getting 2 posters is 25 over 81, which is approximately 31%. In a board game, 3 dice are rolled to determine the number of moves for the players. What is the probability that the first die shows a 6, the second die shows a 6, and the third die doesn't? Okay, well obviously with 3 different die, they're independent from each other, so we don't have to worry about non-replacement or anything like that. So the probability that the first die is going to land on 6 is 1 out of 6. The probability that the second die lands on 6 is 1 out of 6. Now, the probability that the third die, what's it say? Does not. So it needs to land on anything but 6. What's the probability of that happening? 5 out of 6. Multiply those together. Approximately 2%. Or 5 over 216. This is the type of probability that you would probably see on the ACT. Simple probability. Multiplying probabilities. I doubt you would see combinations and permutations on the ACT. Okay, this one we'll do together, and then you're going to start doing some of these on your own. This one shows non-replacement, so we'll do this one together. 10 chips in a bag. 6 of the chips are TV, 3 say vacation, and 1 says car. They're prize chips on a game show. The host is going to draw a chip at random and not replace it, and then he's going to draw another one. What is the probability that he draws vacation, then car? Okay, so let's just talk about the first chip. What's the probability on the first chip that he draws vacation? Alex.
3 out of 10.
3 vacation chips out of 10 total chips. Remember, probability is good over total. We learned that the first day we started talking about probability. Good chips over total chips. Now that chip is out of the bag, sitting there on the desk, table, whatever. And now we say, all right, what is the probability that out of the bag we draw the car chip? 1/9, because there are only 9 chips in the bag. That was confusing first hour for some people. And we multiply those together. If we would have put the chip back in the bag, it would have been 1/10. But since we did not put the chip back in the bag, it is 1/9. That is the part that you have to be cognizant of when you're looking at the problem, whether it's replacement or non-replacement. Okay, 13 out of 52 for the first diamond, 13 out of 51 for the first club with a diamond sitting out, and then 12 out of 50 for the second diamond, because one of the diamonds is sitting out and 2 cards are sitting out that we already drew. So there's what you should be multiplying together. That's big. But that also reduces a little bit and is approximately 1.5%. Okay, for these questions, I've got the answers to all 6. Let's see here. For 13, you would have no 6s would be 5 out of 6 times 5 out of 6, because anything but a 6 is good, which would be 25 out of 36. For 16 and 17, basically the same type of question, the first die you roll, it doesn't matter what you get. So you can't go wrong with the first die you roll. So 1 is what I put there, because 6 out of 6, you can't go wrong. You can roll anything you want on the first die. It's the second one that matters, and 2 of the same number, the second one has to be exactly what the first one was. So it has to be 1 out of 6. Whatever the first one was, the second one has to match it. So for 16, you should have got 1 6. For 17, the first one can be whatever it wants. The second one has to be anything but what the first one was. So I kind of picture myself rolling 1, then rolling the other. So I roll 1, doesn't matter what it is, 6 out of 6. 6 out of 6 things are good. And then the second one, I try to think about what that needs to be. That's how I do those. So for 16, 1 6 is the answer. 1 6 of the time, you're going to get 2 of the same number. And for 17, 5 6 of the time, you're going to get 2 different numbers. Which makes sense, because when you roll 2 dice, you're going to do one of those 2 things. You're either going to get 2 different numbers, or they're both going to be the same. And those 2 add up to 1. If replacement occurs. Well, how many tiles are there up there? 7? How many are consonants? 5. So we got 5 sevenths times 5 sevenths. That's 25 over 49. Which does not simplify. You could come up with a decimal if you wanted to, which would be right around 50%. 21, the probability of x then p if no replacement occurs would be 1 7th times 1 6th, which would be 1 over 42, which would be right around 2% probably. I don't think it reaches 3% level yet. And 23, I think, is 0. Because there's no double letters, are they? And so if you grab a U with no replacement, how in the world are you going to grab another U? To me, that makes no sense. So I'm just going to go with 0 on that one. Answer. I get 1/9, which is around 11%. I changed my probabilities to 1/3. You could have written them as 3/9. That's okay. Mine just looks cooler. 1/3 times 1/3, which is 1/9. Next, what is the probability of getting heads each time a coin? Each time if a coin is tossed 5 times. 1/2 times itself 5 times, 1/2 to the 5th power, which is 1 over 32. So roughly 3% chance of that happening. So 3% of families with 5 kids have 5 straight girls, have 5 girls. Rare. Or boys.